This is Learning Assessment Problem 711. In this circuit we have a single inductor as an energy storage element and a voltage source V of t, which has this waveform shape shown in figure B. It's a pulse which has amplitude of 12 volts between 0 and 1 second, and it is 0 outside those limits. Our problem-solving strategy will be the solution of a first-order transient circuit using the step-by-step approach. In order to be able to identify the time periods which we're working on, we're going to call the interval from 0 to 1 second interval 1, and for times greater than 1 second we'll refer to that as interval 2. So in the first interval, this is the period 0 less than t less than 1 second. We'll go through the 6 steps of the step-by-step approach. During this interval, the source voltage is equal to 12 volts. And the first step is to assume the form of the solution for the VO of t, which is the desired output voltage. So we're going to assume VO1 of t is equal to K11 plus K21 e to the minus t divided by tau 1. So here we have two coefficients K11 and K21 as well as a time constant to be determined. The second subscript here refers to the fact that we're looking at the solution in this interval during which the pulse is at its 12 volt level. Step 2 in the process of finding a solution is to determine the value of the Step 2 in the solution process is to determine the value of the energy storage. Step 2 in the process is to find the initial condition for the energy storage element. In this case, it is the inductor current at time 0 minus, just before this pulse switches to its high level. This is the inductor current that we're looking for. We assume the circuit has been in the steady state up to time 0. We assume the circuit has been in the steady state condition up to time 0. The voltage source has 0 amplitude just before the switching to the 12 volts. And from this we can assume then that the IL at 0 minus is equal to 0. In step 3 we want to determine the initial value of our output variable, that is VO1 of 0 plus. We're going to use the continuity condition for the inductor, that is IL at 0 minus is going to be IL at 0 plus across that switching episode, and therefore VO1 at 0 plus. This inductor current flows down through a 2 ohm resistor, so this is going to be 2 ohms times IL at 0 plus. We just said that that is 2 ohms times 0, so this is equal to 0 volts for the VO1 times 0 plus. Step 4, we want to see what happens as time goes to infinity with respect to our output voltage that we're trying to obtain an expression for, so we want VO1 of infinity. Now, even though the switch condition in the pulsed source operates at 1 second during this interval from 0 to 1 second, we'll just assume that the circuit believes that time will continue on forever in that 12-volt condition. So VO1 of infinity, at that time we assume the circuit would have gone back to a steady state condition. The inductor will look like a short circuit in its steady state or DC condition, and we'll apply a voltage division process to calculate this VO1 at infinity. So we have VO1 at time infinity is equal to, we'll have 2 ohms in parallel with 2 ohms for the voltage across which VO1 so VO1 at time infinity will equal the voltage drop across that 2 ohm resistor pair, which appear in parallel because the inductor is a short circuit. So we have 2 ohms parallel 2 ohms times 12 volts. We're doing the voltage division process, so we have that 2 ohms parallel 2 ohms plus the 2 ohms connected in series with the voltage source. So this is equal to 12 volts divided by 3, which is equal to 4 volts. So we've established that 0 plus voltage at 0 volts and the time infinity voltage at 4 volts. Step 5 is to determine the time constant. We'll call that a toss of 1 for this interval 1. That's going to be L divided by the Thevenin resistance RTH1, which is seen by the inductor in this condition in the circuit. To do this analysis, we set the independent voltage source, which happens to be 12 volts in this period, to 0, and then analyze the remaining circuit for its resistance value. So we have our TH1 is equal to, we have 2 ohms in parallel with 2 ohms plus 2 ohms in series with that parallel combination, or RTH1 is equal to 3 ohms, and time constant 1 is going to be 2 henries divided by that 3 ohms, and that is equal to 2/3 second. In step 6, we put this all together, and we have again our assumed form of the solution. VO1 of t is equal to K11 plus K21 e to the minus t over tau 1. Now VO1 at 0 plus, according to this assumed solution, will equal K11 plus K plus K21, and we've determined from a previous step that this value is equal to 0 volts. Then VO1 at time infinity will be, according to this assumed solution format, will be K11, and we've determined that value to be 4 volts from our previous analysis. So this gives us that K21 is equal to 0 minus 4 volts, or K21 is equal to minus 4 volts. So that combined with the K11 of 4 volts will enable us to put together a solution for this first interval. VO1 of t is equal to 4, 1 minus e to the minus 3t over 2 volts, and this is for the period 0 less than t less than 1 second.